There is a world where the ground is not stone, but fire. These are lava planets, rocky super-Earths, orbiting so close to their stars that their very surfaces boil. By the end of this journey, you will understand 25 incredible facts about the most extreme worlds in the cosmos. We will uncover how they have atmospheres of vaporized rock and why some of them should not exist at all. What do you think it means for a planet to be alive with molten rage? To grasp their nature, we must first define them. A lava planet is exactly what it sounds like: a world where geology is defined not by solid ground, but by a seething ocean of molten rock. Astronomers sometimes call these magma ocean planets. They are rocky exoplanets, often larger and more massive than Earth, that orbit their stars with such shocking intimacy that their surface temperatures soar beyond 1,200 degrees Celsius. That is far hotter than the melting point of rock. At such extremes, the very crust of the planet cannot hold its form. It liquefies, creating a vast, churning global ocean of lava. Picture not a few scattered volcanoes, but an entire hemisphere, or even the whole world, glowing with the angry red light of perpetual sunset. Beneath this roiling sea, scientists believe there may still be a solid core, and above it, a thin, tortured atmosphere not of oxygen or nitrogen, but of vaporized rock and metal, a sky of silicate steam. This makes them utterly alien compared to anything in our own solar neighborhood. We have volcanic moons like Io and planets with molten interiors, but nowhere do we find a world so completely dominated by surface fire. They are not merely hot, they are fundamentally reshaped by heat, existing in a permanent state of geological fury that redefines our understanding of what a planet can be. The discovery of such a world was not just theoretical. In the year 2009, a European space telescope named CoRoT, short for convection rotation and planetary transits, found definitive proof. It spotted a planet orbiting a star roughly 520 light-years away, and this world, named Corot 7b, became the first confirmed lava planet ever identified. This was a monumental moment for astronomy, as it moved these scorching nightmares from the realm of possibility into the catalogue of reality. Corot 7b is a rocky world about 1.7 times the size of our own Earth, but any similarity ends there. It is locked in a blisteringly close dance with its star, completing an entire orbit in just 20 hours. That means its year is shorter than a single Earth day. On its permanent day side, the side forever facing the star, temperatures are estimated to reach a staggering 2,500 degrees Celsius. At that heat, the surface rock doesn't just melt, it sublimates, turning directly from a solid into a vapor, creating that thin, doomed atmosphere of silicate gas. The night side, perpetually turned away, is unimaginably colder, likely a frozen, airless wasteland. The existence of Corot 7b was a shock to the system. It proved that nature could forge planets in conditions we once thought impossible, baking worlds so thoroughly that their geology becomes a fluid, global fire. This single discovery opened the floodgates, teaching astronomers what to look for and confirming that the universe specializes in extremes far beyond our own experience. This extreme proximity forces a strange and permanent relationship. Many of these lava planets are tidally locked to their stars, a gravitational embrace so tight that the planet's rotation perfectly matches its orbit. One hemisphere forever faces the blazing sun, while the other is condemned to eternal night. For a lava planet, this creates a world of absolute extremes. The dayside is a relentless furnace, where heat does not simply melt the surface, it actively vaporizes it, sustaining that global ocean of molten rock. But if you could stand on the night side, you would find a landscape frozen in a profound and airless chill. Here, temperatures could plunge hundreds of degrees below zero, cold enough that the very rock might solidify into a dark, jagged crust. Some theories even suggest that elements vaporized on the dayside could drift across the terminator, the razor-thin line between day and night, and snow out as strange minerals on the frozen surface. This creates an unbelievable dichotomy, a single world split into two realms of utter torment, one bathed in endless fire and the other shrouded in perpetual ice. The Terminator line itself would be a twilight zone of surreal beauty and violence, a place where glowing lava rivers meet frozen shores, where silicate mists might briefly form in the shifting temperatures. It is a border between two impossible worlds, existing side by side on a single, tortured sphere. The heat on these worlds is not merely extreme, it is stellar in its intensity. The permanent dayside of a lava planet can rage at temperatures between 1,500 and over 2,500 degrees Celsius. To grasp what that truly means, consider this: iron melts at 1,538 degrees, and platinum, one of our most refractory metals, liquefies at 1,768 degrees. On these worlds, the very ground is hotter than a blast furnace capable of melting virtually any metal we know. This means the surface is not just a sea of molten rock. It is a churning, incandescent soup where heavier elements like iron and nickel are also liquefied, swirling in vast metallic currents beneath the glowing silicate crust. At the upper end of that temperature range, these metals do not just melt, they boil. They vaporize, rising into the thin, tortured sky to join the silicate steam, creating an atmosphere that could contain clouds of iron droplets and vapors of platinum. It is an alchemist's nightmare, a realm where the fundamental states of matter are rewritten by sheer, relentless energy. This heat is so profound that it rivals the surface temperatures of some of the smallest, coolest stars, the red dwarfs. A lava planet does not bask in sunlight, it is actively cooked by it, its geology erased and rewritten every single moment by a fury that makes our most violent volcanoes seem like gentle campfires. Such intense heat rewrites the very concept of an atmosphere. Forget gentle breezes or water vapor. The air on a lava planet is a seething, toxic brew of vaporized geology. When surface temperatures soar past 2,000 degrees, the solid ground itself begins to boil. This process, called sublimation, turns rock directly into gas, creating a thin and temporary shroud of mineral vapors. The primary component is often silicon monoxide, a gas formed from the most common elements in planetary crusts. Mixed in are vapors of sodium and potassium, elements that vaporize at slightly lower temperatures, adding a strange, metallic tang to the air. But the most astonishing ingredient might be iron. At these extremes, even iron metal can boil, meaning the atmosphere could hold clouds of iron vapor, a sky literally rusting before it rains. This is not an atmosphere in the way we understand it. It is more like the steaming breath of the planet itself, a gaseous echo of its molten surface, constantly replenished as the star's fury strips the world layer by layer. The dynamics of this hellish air are as strange as its composition. These rock vapors, born in the incandescent dayside heat, are carried by ferocious winds toward the eternal night. As they cross the terminator into the freezing darkness, the temperature plummets by thousands of degrees. Here, the vapor can no longer stay aloft. It condenses. Silicon monoxide might solidify into microscopic grains of glass. Sodium and potassium could form eerie, metallic fogs. And that iron vapor, it might literally rain out as droplets of molten metal or snow as fine iron dust onto the frozen, dark landscape. Picture a hailstorm of pebbles made of obsidian, or a slow, silent fall of metallic flakes in the starless void. This creates a bizarre geochemical cycle where the planet is constantly evaporating on one side and snowing rock on the other, a world perpetually cannibalizing and rebuilding itself under the glare of its sun. This bizarre cycle of evaporation and condensation gives rise to one of the most alien weather phenomena imaginable, lava rain. On a world with a vaporized rock atmosphere, precipitation is not made of water. Instead, the skies weep molten stone and metal. Here is how this hellish meteorological system might work. On the scorching day side, the relentless stellar heat constantly boils the surface, pumping silicate and metallic vapors high into the thin, superheated air. If even a tenuous atmosphere exists, ferocious temperature gradients would create powerful winds, screaming from the incandescent hemisphere toward the freezing darkness of the night. These winds act as a conveyor belt, transporting the mineral-laden gases across the terminator line. As this searing vapor hits the sudden, profound cold of the shadowed side, the temperature plummets by thousands of degrees in a matter of kilometers. The gas cannot remain a gas, it must condense. Tiny droplets of molten rock begin to form in the frigid air. Depending on the exact chemistry of the vapor, these droplets could solidify into different minerals as they fall. One possibility is in statite, a common silicate mineral. Another is forsterite, a primary component of the gemstone peridot. So, instead of water droplets, the sky would fill with a mist of incandescent, liquid peridot, or a sleet of dark, glassy particles. On the cooler edges of the terminator, this rain might fall as solid, gritty flakes, a dark snow of crystallized rock. Closer to the dayside, it could descend as a true rain of fire, a shower of sizzling, molten droplets that splash back into the global lava sea. It is a weather cycle of pure geology, where the planet's own skin is evaporated, transported, and then shed back upon itself in a perpetual, violent storm. The universe did not stop with Korat 7b, it offered another, even denser enigma. Enter Kepler 10b, a world discovered by NASA, a planet hunting Kepler space telescope. This was a landmark find, celebrated as one of the very first confirmed rocky exoplanets ever identified, proving that small, solid worlds were not rare cosmic flukes. But its familiarity ends with the word rocky. Kepler 10b is a super-Earth, measuring about 1.4 times the width of our planet, yet it packs a far greater punch. Its mass and size, when calculated together, reveal an astonishing density. This world is incredibly heavy for its volume, a clue that points to a composition utterly drenched in iron. Scientists believe it could be made of up to 80% iron by mass, a staggering figure when you consider Earth's core is only about 32% iron. The rest of the planet is likely a mantle of silicate rock, but here is the catch. It orbits a sun-like star so closely that its year is a blistering 20 hours long. Surface temperatures on its day side are estimated to exceed 1,300 degrees Celsius, more than hot enough to melt rock into a global lava ocean. So we are left with a bizarre planetary portrait, a world that might be structured like a colossal ball bearing. At its heart could lie a solid core of iron, unimaginably large and dense, while wrapped around it is a churning, incandescent shell of molten silicate. This raises a haunting question. What catastrophic event could forge such an iron-rich world? Could it be the stripped remnant of a much larger planet, its outer layers boiled away by the star, leaving behind this metallic heart? Or was it born from a protoplanetary disk already rich in heavy elements? Kepler 10b stands as a scorched monument to the violent and diverse processes of planetary formation. But the cosmic record for orbital intimacy is held by an even more baffling world. Kepler 78b is a planet that defies every expectation, a rocky super-Earth locked in a dance of such impossible closeness that its very existence is a profound mystery. This world completes an entire orbit around its star in just 8.5 hours. Its year is shorter than a single work shift on Earth. At that distance, the surface temperature soars to an estimated 2,300 degrees Celsius, ensuring its surface is a global ocean of molten lava. Yet the real puzzle is not its heat, but its survival. A star like the one Kepler 78b orbits goes through a phase in its youth where it swells to a much larger size, a stage called the subgiant branch. Based on our understanding of stellar evolution, when this star expanded billions of years ago, its outer atmosphere should have completely engulfed the orbit where Kepler 78b now resides. The planet, in its current position, would have been inside the star itself, subjected to unimaginable drag and friction. It should have spiraled inward and been utterly vaporized, consumed by the very sun it now orbits. So how is it still here? This is the central, thrilling contradiction. Astronomers are left with two equally dramatic possibilities. The first is that the planet somehow survived this stellar engulfment, a scenario that seems nearly impossible, like a moth flying through a bonfire and emerging unscathed. The second, and more favored theory, is that Kepler 78b was not born in this scorching neighborhood. It may have formed much farther out in the cooler reaches of its planetary system, and then, through complex gravitational interactions, migrated inward long after the star had settled into its current, more stable size. This inward spiral, however, must have stopped with exquisite precision, parking the planet in an orbit that skims the stellar surface without crossing the final, fatal threshold. Kepler 78b stands as a stark reminder that our models of planetary birth and migration are still incomplete, challenging us to explain how a world can live in a place where it should have died long ago. The Kepler Space Telescope was the key that unlocked this vault of scorching worlds. Its mission was simple in concept, yet revolutionary in practice: to stare unblinkingly at a single patch of sky containing over 100,000 stars, searching for the telltale dimming caused by a planet passing in front of its sun. This transit method was exquisitely sensitive to planets on tight, fast orbits. A world like Corot 7b or Kepler 78b, with a year measured in hours, would cross the face of its star frequently, creating a rhythmic, easily spotted signal in the data. Kepler was not just looking for planets, it was conducting a cosmic census, and what it found reshaped our galactic perspective entirely. The telescope revealed that short-period, rocky planets orbiting perilously close to their stars are not rare anomalies. They are a common feature of the Milky Way. For every star like our Sun, there is a significant chance it hosts a blistering, compact world dancing just a hair's breadth from its fiery embrace. This statistical revelation was profound. It meant that the calm, orderly architecture of our own solar system, with small rocky planets safely distant from the Sun, is just one possible configuration among many. The universe, it seems, has a fondness for forging these intimate, violent relationships between star and planet, creating entire classes of worlds that we never knew existed until we had the tools and patience to look. Kepler showed us that the cosmos is not only stranger than we imagined, but that its most common blueprints often include chapters written in fire. The sheer variety of these scorched worlds is as astonishing as their existence. Among them, K2141b stands out not just for its fury, but for the detailed portraits scientists have painted of its hellish cycles. This planet, roughly 1.5 times the size of Earth, offered a rare gift to astronomers, a spectrum. By analyzing the starlight filtering through its atmosphere during a transit, researchers detected the chemical fingerprints of specific vapors. They found an atmosphere dominated not just by silicon monoxide, but also by sodium and silicon dioxide vapor. This was like getting a direct weather report from a world of fire. With this chemical data in hand, scientists could construct a terrifyingly precise model of its global systems. The model reveals a planet caught in a relentless, supersonic geochemical loop. On the permanent day side, temperatures soar beyond 3,000 degrees Fahrenheit, vaporizing the surface rock into the detected gases. These vapors are then ripped away by howling winds, estimated to scream across the terminator at speeds exceeding 4,000 miles per hour, far faster than the speed of sound on Earth. These supersonic gales carry the mineral-laden air into the freezing darkness of the night side, where temperatures plunge to negative 300 degrees Fahrenheit. There, the silicon monoxide and silicon dioxide condense directly from vapor into solid rock, falling from the sky as a gritty, obsidian snow, but the cycle does not end in that frozen silence. The model suggests this accumulated rock snow forms a vast, sluggish glacier. Driven by the planet's immense gravity, this glacier of solid stone slowly oozes back toward the searing dayside. As it crosses the terminator line, the brutal heat reclaims it, melting the rock glacier back into the global lava ocean, ready to be vaporized once more and continue the endless, violent loop. This makes K2141b a world with a literal rock cycle, where the very ground is evaporated, transported, frozen, and recycled in a perpetual storm of geology. The ground beneath that roiling ocean of fire holds a familiar, yet profoundly transformed, secret. While their conditions are alien beyond belief, the fundamental building blocks of lava planets are surprisingly ordinary. Based on precise measurements of their mass and size, which give us their density, scientists infer that these scorched worlds are made of the same basic ingredients as Earth, Mars, or Venus. They are constructed primarily from silicates, the rock-forming minerals that make up the bulk of our own planet's crust and mantle. Think of minerals like olivine, a greenish crystal found in Earth's upper mantle, or pyrozene, common in volcanic basalt. On a lava planet, these are not solid stones, they are the constituents of the global molten sea. The other key component is iron, the heavy element that gives our planet its magnetic field and dense core. The extreme, relentless heat plays a crucial role in organizing this chaos. In the furnace of a young lava planet, the entire world was likely molten from surface to center, a true magma ocean. In this white-hot soup, physics takes over. Heavier elements like iron and nickel sink through the liquid rock, pulled by gravity toward the planet's heart. This process, called planetary differentiation, is how Earth formed its own metallic core billions of years ago. On a lava planet, it creates a dense, solid, or possibly molten, iron-rich core at the center. Meanwhile, the lighter silicate minerals, the rocky slag of this cosmic smelting, float upward to form the churning mantle and, ultimately, the vaporized atmosphere. So the terrifying spectacle of a lava world is, in essence, a planetary anatomy lesson in fast forward, a visible demonstration of the same sorting process that happened deep inside our own, cooler Earth. The fire does not change the ingredients, it simply reveals the recipe with brutal, incandescent clarity. This journey from the cold outer reaches to the inner inferno is the key to their existence. How does a planet end up in an orbit so tight it should have been consumed by its star? The answer lies in a dynamic and often violent process called planetary migration. In the early, chaotic days of a planetary system, worlds are not fixed in their orbits. They can drift, pulled by powerful gravitational forces. One major driver is the protoplanetary disk itself, the vast swirl of gas and dust from which planets form. As a young planet moves through this dense material, it creates gravitational wakes, like a boat plowing through water. This interaction can sap the planet's orbital energy, causing it to lose momentum and slowly, inexorably, spiral inward toward the star over millions of years. This type of migration might explain the existence of hot Jupiters, gas giants found absurdly close to their suns. But what about rocky lava planets? Their story might be even more dramatic. One compelling theory suggests that some of these scorched worlds are the naked, skeletal remains of former gas giants. Imagine a planet like Jupiter migrating too close to its star. The blistering stellar radiation and fierce stellar winds could have violently stripped away its entire thick hydrogen and helium atmosphere, leaving behind only the dense, rocky core that once lay at its heart. This exposed core, a super-Earth rich in iron and rock, would then continue to orbit in that scorching neighborhood as a lava planet. Alternatively, a rocky world might have formed much farther out, in a region where water and other volatiles could exist, only to be gravitationally kicked inward by a clash with another planet, a cosmic billiard shot that sent it careening toward the fire. This migration theory solves the paradox of worlds like Kepler 78b, placing them in orbits they could never have been born in, yet somehow survive within. Could a world of fire have a companion? The idea of a moon orbiting a lava planet seems like a fantasy, a tiny refuge circling a sphere of perpetual fury. Yet the question forces us to consider the brutal physics of such an extreme environment. The first and greatest challenge is gravity's relentless grip. A lava planet orbits so close to its star that the sun's tidal forces are monstrous. These forces would actively work to destabilize any wide, delicate orbit a moon might attempt. They could either pull a moon away, sending it spiraling into the star, or crush it inward, causing a catastrophic collision with the planet itself. Furthermore, the violent migration that likely delivered the lava planet to its scorching birth would have been a chaotic journey, scattering or destroying any original satellites in the process. Given these titanic forces, the existence of a traditional, long-lived moon seems profoundly unlikely, but the cosmos has a talent for surprise. Theoretical models suggest narrow pathways where a moon might persist. One scenario involves a captured asteroid. If a small, dense rocky body ventured too close to the lava planet during its migration, or after it settled into its hellish orbit, the planet's gravity could theoretically snare it, locking it into a tight, fast orbit. This would not be a serene companion like our own moon, but a captive, doomed to skim the upper reaches of the planet's vaporized rock atmosphere. Another, even more speculative, possibility is a moon that formed with the planet far out in the cooler protoplanetary disk, before the Great Migration inward. If this moon's orbit were exceptionally stable and close to its planet, it might have survived the inward spiral, clinging to its host like a passenger on a ship sailing into a supernova. The survival would be a delicate, precarious miracle. The experience of such a moon would be a study in absolute extremes. Tidally locked to its planet, one side would forever face the incandescent lava world below. This hemisphere would be bathed not only in the blinding light of the nearby star, but also in the intense infrared glow radiating from the planet's molten surface. This secondary heating could be enough to melt rock on the moon's own surface, creating a localized sea of lava solely from the planet's radiant heat. The other side, turned away, would gaze into the eternal cold of space and the star's distant glare. It might be a frozen, airless wasteland, a stark twin to the planet's own dark side. The moon would straddle a line between two sources of torment, roasted by its primary and baked by its planet, a testament to the complex and unforgiving relationships that define these scorched systems. The temperature difference between these two hemispheres is not just a matter of degree, it is a chasm of thermodynamic impossibility. On the permanent day side, rock vaporizes at 2,500 degrees Celsius. Just over the horizon, on the eternal night side, temperatures could plunge to -200 degrees or even lower, a cold so profound it would freeze the very air out of the sky if any existed. This is not a gentle gradient from summer to winter, it is a sheer cliff, a temperature drop of nearly 3,000 degrees occurring over a distance that could be as short as a few hundred kilometers. Such a staggering imbalance of heat creates an engine for atmospheric violence on a scale we can scarcely comprehend. Any tenuous atmosphere of vaporized rock would be caught in this relentless tug of war. The superheated gas on the day side expands violently, creating a region of extremely low pressure. The freezing, dense air on the night side would rush in to fill that void. The result would be winds of unimaginable ferocity, screaming from the frozen darkness into the blazing light at speeds that could exceed several thousand miles per hour. These are not winds in any earthly sense. They are supersonic shockwaves of gaseous rock, a permanent planetary jet stream fueled by stellar fury. This constant, violent circulation might coalesce into a single, stable, and terrifying weather feature, a planet-encircling hurricane parked directly over the Terminator line. This storm would not be made of water clouds and rain, but of silicate vapors and molten mineral droplets, a maelstrom of incandescent mist and dark, gritty hail, forever raging in the twilight where fire meets ice. Modeling such a climate pushes our best supercomputers to their limits, because the physics involved operates in regimes we have never directly observed. The gases are exotic, the temperature range is absurd, and the wind speeds approach those found in stellar atmospheres. It is a reminder that on these worlds, even the weather is a form of geology, a relentless, screaming wind that shapes the planet as surely as any river of lava. This relentless stellar assault is not a temporary condition. It is a death sentence written across billions of years. The fate of a lava planet is to be slowly, methodically, torn apart by its own sun. The process has a name: photoevaporation. Imagine the star's radiation not just as light and heat, but as a torrential, unending solar wind, a stream of high-energy particles screaming into space. For a planet orbiting at such a perilous closeness, this wind hits like a cosmic sandblaster, but one that strips away not dust, but the very atoms of the planet itself. The extreme ultraviolet and X-ray radiation from the star packs enough punch to rip molecules apart and give individual atoms such violent kicks that they achieve escape velocity, flying off into the void forever. This photoevaporation first targets the planet's atmosphere, that thin shroud of vaporized rock. The stellar wind constantly shears it away, carrying the silicate and metallic vapors off into space. But the process does not stop at the atmosphere. With no protective magnetic field or thick blanket of air to shield it, the planet's molten surface is directly exposed. Over astronomical timescales, the combined effect of the radiation and the stellar wind can begin to ablate the surface itself, literally blowing the planet away layer by layer, molecule by molecule. This leads to one of the most dramatic hypotheses in exoplanet science, the evaporating core scenario. Astronomers studying some of the very densest, fastest orbiting worlds have proposed a terrifying origin story. What if a planet like Kepler 10b, that astonishingly iron-rich super-Earth, was not born that way? What if it started its life as a much larger, more typical rocky planet, perhaps several times the mass of Earth, with a substantial rocky mantle surrounding a smaller iron core? Then, over billions of years of relentless photoevaporation, the star systematically stripped away the entire outer mantle, the entire rocky shell of the planet. The lighter silicate materials vaporized and were carried off by the stellar wind, leaving behind only the dense, heavy, metallic heart that could best resist the erosion. In this view, these ultra-short period lava planets are not worlds in their prime. They are planetary corpses, the skeletal iron cores of giants that were completely devoured. They are the stark, scorched tombstones of planets that once were, orbiting in the graveyard of their own evaporated remains. Their slow evaporation forces us to ask a deeper question: what exactly makes a world a world? These lava planets exist in a permanent state of violent transformation, challenging the very definitions we use in planetary science. We often speak of the habitable zone, that Goldilocks region around a star where liquid water could exist on a surface. But lava planets show us that habitability is just one narrow chapter in a much larger and more brutal book of planetary existence. They force astronomy to expand its vocabulary beyond comfort and into the realm of pure, extreme physics. By their very nature, they are not meant for life as we understand it, yet they are invaluable. They serve as cosmic laboratories, testing our theories under conditions we could never replicate on Earth. Observing how a planet behaves when its surface is hotter than a steel mill's crucible teaches us fundamental truths about the behavior of materials, the limits of geological processes, and the ultimate fate of worlds that stray too close to their suns. They refine our models, showing us that a planet is not defined by its potential for life, but by its capacity to exist under a staggering range of conditions. In doing so, they stretch the meaning of the word planet itself, from a static, stable globe to a dynamic, evolving entity that can be a molten orb, a vaporizing cinder, or a frozen, airless rock, sometimes cycling between these states on a single, tortured sphere. They remind us that the universe is not obligated to produce gentle worlds, and that understanding the extremes is just as crucial as seeking the familiar. The future of understanding these worlds is already taking shape, and it bears a golden mirror. The James Webb Space Telescope, humanity's most powerful eye on the infrared universe, is perfectly engineered to pierce the mysteries of lava planets. While previous telescopes could only infer their existence and basic properties, Webb sees in the exact type of light that these scorching worlds emit most strongly. Its observations will transform our speculative models into concrete, detailed knowledge. The primary tool is transmission spectroscopy. When a lava planet transits its star, A tiny fraction of the star's light filters through the planet's thin, vaporized atmosphere. Different molecules in that atmosphere absorb specific colors or wavelengths of that light. Webb's exquisite sensitivity can catch these minuscule fingerprints. It will not just confirm the presence of an atmosphere, it will read its chemical recipe, identifying the exact ratios of silicon monoxide, sodium, potassium, and even metal vapors like iron. This is the difference between guessing a soup has salt and knowing it contains precisely 2 grams of sea salt, a gram of black pepper, and a hint of smoked paprika. Beyond mere ingredients, Webb aims to map the temperature of these worlds in stunning detail. By observing the planet's heat glow as it orbits, moving from dayside to nightside, the telescope can create a thermal map. We will see the precise gradient of that infernal furnace, pinpointing where the lava ocean is hottest, how sharply the temperature plummets at the terminator, and just how cold the eternal night truly becomes. This data will directly test our models of supersonic winds and global rock cycles. The ultimate goal is to detect specific, unexpected molecules. Could there be traces of water vapor, a relic from the planet's formation before it migrated inward? Could complex silicate chains form in that violent sky? Each observation will be a revelation, turning these points of light into worlds with known weather, confirmed chemistry, and a story we can finally begin to read in the language of physics itself. That violent, ongoing transformation holds a secret key to our own distant past. To understand where planets come from, we sometimes need to look at worlds stuck in a state of perpetual birth. Lava planets, in their endless, fiery churn, act as cosmic time capsules. They offer us a living snapshot of a phase that every rocky world, including our own Earth, went through but quickly left behind. In the first 100 million years of its existence, Earth was almost certainly a global magma ocean. Cataclysmic impacts from leftover planetary building blocks delivered immense heat, while the decay of radioactive elements trapped deep within kept the entire young planet molten from the surface nearly to the core. This was not a calm, blue marble, but a seething, incandescent sphere, a world of fire not unlike the lava planets we see today orbiting distant stars. The crucial difference is time. Earth cooled, its magma ocean solidified, its crust formed, and its geology evolved into the complex, layered planet we know. A lava planet, however, is trapped. The constant, furious heat from its nearby star prevents it from ever cooling down, locking it in that primordial, molten state indefinitely. This gives scientists an unprecedented opportunity. By studying the atmosphere of a vaporized rock world, we are effectively sampling the gases that would have bubbled out of Earth's own ancient magma ocean. We call this process outgassing. As our planet's magma churned, dissolved gases like water vapor, carbon dioxide, and nitrogen were released, rising to form the very first blisteringly hot atmosphere. A lava planet's silicate steam sky is a direct, if more extreme, analog to this. Observing its composition tells us what kinds of gases a molten silicate world naturally produces, helping us reverse engineer the recipe for Earth's own early air. Furthermore, the relentless differentiation we see in action on a lava planet, with heavy iron sinking to form a core, is the same process that shaped Earth's interior billions of years ago. Watching it happen in real time, so to speak, through the lens of planetary models constrained by telescope data, refines our understanding of how quickly cores form, how magnetic fields might be generated in such an environment, and how the final chemical makeup of a planet's mantle is determined. So, while we cannot travel back in time to witness Earth's fiery infancy, we can look across the galaxy at these stalled, scorched worlds. They are not just freaks of nature, they are preserved laboratories of planetary adolescence, holding frozen-in-time clues to the violent and foundational processes that built our own home. But our search for these worlds of fire must look beyond stars like our own Sun. Most of the lava planets we have found so far orbit G-type stars, similar in size and temperature to the Sun. Yet the most common stars in our galaxy are not yellow like ours. They are the dim, red embers known as M-dwarfs or red dwarfs. These stars are smaller, cooler, and far more long-lived. Around such a star, the conditions for creating a lava planet shift dramatically. The habitable zone, where liquid water could exist, is already incredibly close to a red dwarf. The zone where rock melts, the lava planet zone, would be closer still, a tight, blistering hug just a few million miles from the stellar surface. A rocky world in this orbit would be so close that it would almost certainly be tidally locked. One hemisphere forever facing the dim red sun and the other in endless night. But the environment around a red dwarf is anything but calm. These small stars are notorious for their violent tempers. They frequently unleash massive stellar flares, sudden eruptions of radiation that can double the star's brightness in minutes. For a planet orbiting in that intimate lava zone, a flare would not be a distant light show. It would be an apocalyptic event. The planet's tenuous atmosphere of vaporized rock would be hit by a wave of X-rays and ultraviolet radiation so intense it could blast portions of that atmosphere clean off into space. The surface itself might flash heat even further, churning the global lava ocean with new fury. This presents a radically different kind of extreme. While a lava planet around a sun-like star faces constant, relentless baking, one around a flaring red dwarf endures a punctuated hell, periods of searing equilibrium shattered by bursts of stellar violence. Studying such a world, if we can find one, would teach us not only about planetary geology under fire, but about planetary resilience. Could a world maintain a stable lava ocean and rock vapor atmosphere in the face of such periodic atmospheric stripping? The search is already underway, pushing our detection methods to their limits to find these tiny, fast-orbiting worlds against the flickering glow of the galaxy's most common stars. Those vivid artistic impressions of lava planets are not just beautiful, they are a crucial part of the story. You have likely seen them, dramatic vistas of glowing orange seas under a dark, starry sky, with great rivers of fire carving channels through black, crusty landscapes. These illustrations are born from a powerful collaboration between the cold numbers of science and the boundless reach of human imagination. Artists take the data, the mass, the orbit, the estimated temperature, and they give it a face. They translate abstract equations into a world we can visualize, making the incredible feel tangible. Yet the scientific reality, built from physics and chemistry, is often stranger than any painting can fully capture. The surface of a typical lava planet is not likely to have distinct rivers or recognizable landforms. At temperatures exceeding 2,000 degrees, the molten rock behaves less like thick honey and more like a very hot, low-viscosity fluid, perhaps closer to water in its flow. It could be a single, global, churning ocean with no solid shore in sight, a sphere of liquid fire where any temporary crust that forms is immediately remelted by the stellar fury. And above that ocean, the sky would not be clear and starry. It would be choked with a dense, glowing fog, a mist of vaporized rock and condensing mineral droplets that obscures the sun and scatters its light into a permanent, hellish twilight. The artists give us a gateway, a breathtaking glimpse of the impossible. But the scientists remind us that the true nature of these worlds is written in the language of extreme fluid dynamics and plasma physics, a reality both more alien and more fascinating than we could ever dream up on our own. This partnership is essential, for without the numbers, the art is just fantasy, and without the art, the numbers remain locked away, a secret the universe tells only to those who can translate its math into majesty. Landing on a world of fire is the ultimate engineering nightmare. The surface of a lava planet is not a landscape to be touched. It is a thermodynamic force that would annihilate any probe we could build today. Consider the most heat-resistant materials we possess. The tiles on a space shuttle's belly can withstand around 1,600 degrees Celsius for re-entry. The heat shields on probes that have plunged into the sun's atmosphere are designed for slightly higher extremes, yet the dayside of a lava planet exceeds 2,500 degrees, a temperature that would reduce those shields to puddles in seconds. There is no passive material, no superalloy or advanced ceramic that could simply sit on that surface and survive. The rock itself is molten, so there is no solid ground to anchor to, only a shifting, incandescent sea. Any structure would need to float, all while being bathed in a heat more intense than a welding torch. For a fleeting moment, you might dream of active cooling, a system that constantly circulates a refrigerant to carry the insane heat away from the probe's core. But the energy required would be colossal, and the heat sink, the place to dump all that stolen thermal energy, would be the already superheated environment around it. It is like trying to cool a house by opening the refrigerator door while the building is engulfed in flames. The physics itself seems to conspire against the very idea of contact. So for now, and for the foreseeable future, a landing is firmly in the realm of science fiction. Our exploration must be one of careful, distant observation. The realistic path forward lies with hardy orbiters or daring flyby probes. Imagine a spacecraft designed not to land, but to skim the searing upper atmosphere. Shielded by a revolutionary reflective barrier, it could dip briefly into that silicate steam, sampling the gases directly before swinging back out to safety. Or picture a robust orbiter, positioned at a safe distance, equipped with instruments that never need to touch the inferno. It could map the planet's heat glow in exquisite detail, charting the lava ocean's currents by tracing temperature variations. It could use spectrometers to analyze the light filtering through the atmospheric vapors during each transit, building a daily weather report for a world of rock storms. These missions would be triumphs of indirect exploration, learning everything about the planet by studying the energy it emits and the light it steals from its star. They would be our eyes where our hands can never go, unraveling the secrets of these blazing worlds from the only place we can survive, the cold, quiet dark of space. The label Hell Planet reveals more about us than it does about these distant worlds. It is a human judgment, born from our innate understanding that life, as we know it, could never survive there. But the cosmos operates on a different scale of value, one measured in physics, chemistry, and raw, beautiful process. From a purely scientific perspective, these are not nightmares, they are masterclasses. They represent one extreme end of the vast planetary spectrum, just as an ice giant like Uranus shows us how a world can be built from slushy ices and hydrogen far from a star's warmth. A lava planet demonstrates the opposite limit, a world sculpted entirely by proximity and fire. Their existence is not a cosmic mistake, it is a vital data point. Imagine trying to understand climate by only studying temperate spring days, or geology by only looking at sandstone. You would miss the entire story. Lava planets force us to complete the picture. They show us what happens when every dial is turned to maximum, when heat and gravity and stellar radiation operate without the moderating influence of water, air, or a protective magnetic field. In their relentless churn, we witness the fundamental behavior of planetary materials under the most intense stress. Their vaporizing surfaces teach us about atmospheric escape. Their molten iron cores, real or hypothesized, instruct us on planetary differentiation. Their very survival in orbits of impossible closeness challenges and refines our models of orbital migration. To call them merely hellish is to overlook their profound contribution. They are natural phenomena of stunning extremity, and by studying them, we do not just catalog freaks, we enrich our understanding of the entire menu of possibilities the universe can cook up. They remind us that diversity is the rule, not the exception, and that even in the furnace, there is a terrible, illuminating elegance. This search for familiar ground leads us back to our own cosmic neighborhood. While our solar system holds no true lava planets, it offers two fascinating, if imperfect, mirrors. The first is Mercury, the innermost planet. Baked by the sun, its dayside temperatures soar to 430 degrees Celsius, hot enough to melt lead but far too cool to melt silicate rock. It is a scorched, airless world, not a molten one. Yet, its heavily cratered surface and large iron core hint at a violent past. Scientists believe that in its earliest days, Mercury may have been the victim of a colossal impact, one so powerful it stripped away much of its original rocky mantle and left the entire surface a temporary magma ocean. As that ocean cooled and solidified, it gave Mercury the dense, iron-rich composition and the ancient, scarred face we see today. In this way, Mercury might be a fossilized snapshot of a phase that exo-lava planets are trapped in forever, a glimpse of what comes after the fire, if the fire ever stops. For a living example of planetary-scale volcanism, we must look not to a planet, but to a moon. Orbiting Jupiter is Io, a world caught in a perpetual gravitational tug-of-war. Heated not by the sun, but by the immense tidal forces from Jupiter and its sibling moons, Io is the most volcanically active body in our entire solar system. Its interior is constantly kneaded and stretched, generating immense friction that melts rock from within. The result is a global network of over 400 active volcanoes, colossal lava lakes that span hundreds of kilometers, and rivers of molten silicate that flow across its mottled yellow surface. Plumes of sulfur and sulfur dioxide gas erupt hundreds of kilometers into its thin atmosphere, a sky stained by its own geological fury. Io is not a lava planet. Its heat source is internal and tidal, not stellar. Yet, it is our only local laboratory for studying the extreme processes that might define an exo-lava world. By observing Io's lava lake behavior, how its crust reforms over molten pockets, and the chemistry of its volcanic plumes, planetary scientists can test models of magma ocean dynamics and atmospheric formation. The violent resurfacing of Io, where a landscape is erased and rewritten in a matter of decades, shows us what a world looks like when geology is a constant, global, and surface-level event. It is the closest analog we have, a hyperactive volcanic proxy whispering clues about the churning, incandescent oceans on worlds light-years away. Supercomputers are the time machines and pressure chambers for these unreachable worlds. Since we cannot send a probe into that inferno, scientists build digital replicas inside the most powerful computers on Earth. These are not simple animations. They are intricate virtual laboratories governed by the precise laws of physics. Every simulation begins with a set of starting conditions, a recipe based on the scant data we have from telescopes, the planet's mass, its orbit, the type of star it circles. Then, the supercomputer unleashes its calculating power. It divides the planet into millions of virtual cells, each one a tiny box of simulated material. The program then asks what happens next. It calculates the flow of heat from the core to the surface, the churning convection in the magma ocean as hotter rock rises and cooler, denser material sinks. It models how vaporized rock might rise from that molten sea, forming a thin, superheated atmosphere. Then comes the weather. The simulation introduces the staggering temperature difference between day and night and watches as physics takes over. It calculates how the vaporized rock gas expands on the day side and contracts on the night side, generating those supersonic winds screaming across the terminator. It tracks how silicate and iron vapors condense as they hit the cold, potentially creating virtual lava rain and metallic snow. These models can run for millions of simulated years in a matter of days, allowing researchers to watch the long-term fate of a lava planet unfold. They can test the photoevaporation hypothesis, seeing if a planet with a certain composition would indeed have its outer layers stripped away over billions of years, leaving behind a dense iron core. They can experiment with different interior structures, asking if a solid core exists or if the entire planet is molten, and what signature each configuration would leave in the planet's orbit or heat emission. Each simulation is a question posed to the universe, and the result, whether it matches our telescopic observations or not, teaches us something profound. A mismatch means our assumptions are wrong, and we must go back, tweak the recipe, and run the experiment again. A match is a thrilling moment of validation, a sign that our virtual hellscape might just reflect a reality trillions of miles away. In this quiet room filled with humming servers, the most violent planets in the galaxy are born, live, and die, over and over, teaching us their secrets one calculation at a time. These blazing worlds cast our own home in a startling new light. The very existence of lava planets, so common in the galactic census, delivers a humbling and profound message about our place in the cosmos. Their prevalence suggests a startling possibility that our own calm, ordered solar system might be the exception rather than the rule. We grew up with a model of planetary architecture that seemed sensible, almost inevitable: small rocky worlds close to the sun, gas giants in the middle distance, and icy bodies in the far reaches, all moving in stable, well-spaced orbits for billions of years. It felt like a natural, even peaceful, progression. But the galaxy, it seems, has a taste for drama. The countless lava planets and hot Jupiters we have found tell a different story, one of chaos, migration, and violent rearrangement. They show us that planetary systems are not born in their final configuration. They are dynamic, often tumultuous places where gravitational shoves can send worlds spiraling inward toward fire or outward into the frozen dark. Our solar system's serene stability is not the default setting of the universe. It might be a rare and fortunate outcome, a quiet backwater in a galaxy filled with scorching, intimate dances between star and planet. This realization reframes our own history. Perhaps we owe our existence to a lack of drama, to the fact that no runaway gas giant migrated inward to scatter the rocky planets, or to a protoplanetary disk that dissipated before such chaos could begin. The lava planets are a testament to the universe's boundless creativity. its ability to forge worlds in conditions we once deemed impossible. They stretch the canvas of what a planet can be, proving that the cosmic menu is far more extensive and extreme than the single, gentle example we call home. In their perpetual fury, they remind us that our blue marble is not just special, it is miraculously, precariously serene, a single, quiet verse in an epic poem written mostly in fire. Our journey across these 25 mind-bending facts has taken us from the first discovery of Korat 7b to the violent weather cycles of K2-141b. We have seen how tidal locking splits these worlds into realms of permanent fire and eternal ice, creating supersonic winds that scream across the Terminator. We have learned that their skies are not filled with air, but with the vaporized breath of rock and metal, condensing into lava rain and metallic snow. The mystery of their very existence was unraveled by the theory of planetary migration, a dramatic inward spiral that leaves them baking in orbits where they could never have been born. While these environments are terrifying beyond human experience, they are not cosmic mistakes. Each scorching fact, from evaporating iron cores to possible rock glaciers, stretches the boundaries of what we thought a planet could be. They prove the universe is a laboratory of extremes, capable of forging realities far stranger than our fiction. The future of this exploration shines with the golden mirror of the James Webb Space Telescope, which will transform these points of light into worlds with known weather and confirmed chemistry. Every new observation will test our boldest models and likely reveal surprises we cannot yet conceive. So, as we leave these oceans of fire behind for now, we turn the question to you. Which of these 25 facts reshaped your view of the cosmos the most? Was it the planet that orbits its star in just 8.5 hours, or the idea of a sky weeping molten gemstones? Share your thoughts below, and if you crave more journeys to the edges of understanding, subscribe and join us as we delve into the next great space mystery.